Okay, y'all, so I'm going to go through how to solve these problems, these practice exam problems that I posted earlier today, or that I went through earlier today. I'll be posting them shortly to kind of correspond with this video. So without further ado, let's go ahead and get started. Question number 1 asks about what volume of magnesium hydroxide would be required to react or neutralize with hydrochloric acid. Here you have two things. You have magnesium hydroxide and hydrochloric acid. Two things means it's not a dilution. That means no M1V1 equals M2V2 will be allowed, like, at all. And I try to never use that equation in class anyway, so you'll come across it in lab whenever you dilute something, meaning you add water to it. But in this case, that is not one of those situations, so don't do it. All right, let's go ahead and get started. So magnesium hydroxide reacting with hydrochloric acid tells you it's an acid-base reaction. Hydrochloric acid is HCl. This is an acid. It's reacting with magnesium hydroxide, which would be a base. Anything with hydroxide here is going to be a base. And it's going to form the H plus and the OH minus of the hydroxide form water. But we have two waters, therefore we're going to need two H pluses. And that will create two waters. So we got two OHs, two H pluses to form two waters, and then you just put whatever is left. Well, we have magnesium left, and we happen to have two chlorides left. And that works out really well because magnesium chloride is MgCl2. So this is our reaction right now. Another thing we should have noticed is the fact that it says 75 milliliters and 0.110 mole per liter. You'd put that into liters, so this would be 0.075 liters times 0.110 mole per liter to give you the number of moles of hydrochloric acid. In this case, the number of moles of hydrochloric acid is 0.00825 mole, which we can put here. So now it's getting to be a pretty straightforward yield problem almost. We have the number of moles here, we're looking for the moles there. All we do is get started, so 0.00825 mole of HCl. We know for every 2 mole of HCl, we get 1 mole, or we require 1 mole of magnesium hydroxide. Now that's great, but the question says what volume. So we're trying to get to volume, but there's a piece of information we haven't used. It's this. We know that we change big M into mole per liter, so we're essentially saying we got 0.210 mole per liter of this magnesium hydroxide. Well, that's good because we've got moles of magnesium hydroxide here. This is mole of magnesium hydroxide. This is also mole of magnesium hydroxide. So we can match it. There's 0.210 mole of magnesium hydroxide and a liter of magnesium hydroxide. And if you take 0.00825 divided by 2 divided by 0.210, you get an answer of 0.0196 liters, which would be 19.6 milliliters. Now we can move on to the next one. Question 2. It's a pretty straightforward dilution calculation. Hey, dilution! Yay, you can use M1V1 equals M2V2 should you choose. The problem is you just have to figure out what's M1V1 and M2 and V2. Or you can think through it logically, which I like to do anytime over the alternative. So we're gonna go ahead and start with, essentially, we got a 50.00 milliliter of solution, and we did not have any idea the concentration, but we know when we took that and we poured it in another container and we filled it to 0.225 liters, and 50 milliliters I probably should have written as 0.0500 liters. I like to put things immediately into liters. When we filled it up here, we knew that its concentration after dilution was 0.110 mole per liter. In this situation, this would tell us, when you multiply them together, anytime you have liters and moles per liter, you multiply them together, that we had 0.025 0.2475 mole of this stuff. Doesn't even matter what it was. So in this container we have 0.02475 mole. And when we went from here to here, all we added was water. So essentially we put this in here and then we added water until it got here. Well, every single mole that is in here had to have originally also come from here. In other words, we also in this one had to have had 0.02475 mole in this one. Well, the question is, what was the concentration of this prior to dilution? Well, we know how many moles there were. We know how many liters there originally were. All we do is put moles over liters. So 0.02475 mole divided by 0.0500 liters. And it gives me an answer that I apparently did not write down. So you can figure it out. Moving on, number 3. A light bulb was connected to a circuit, and the prongs of each end of the circuit were placed in a beaker of water. Which of the following would allow the light bulb to light the brightest? Well, essentially what we're looking for right now is electrolytes. Electrolytes are things that dissolve in water into ions. So we're looking for the things that break into ions. And the greater the ions, the greater the electrolyte. In other words, if you have lots of ions, we'll have a better electrolyte. So let's go ahead and look at each of these. They're all 0.5 moles, so we're starting off with the same amount of moles of each one. But this one breaks down into 2 sodiums, 2 Na pluses, and 1 sulfate, SO4, 2 minus. Each of these would be dissolved in water. This is soluble. This one right here, this chlorous acid would break into H plus and ClO2 minus. However, it's important to note that this is a weak acid, meaning it's going to have a double arrow. It's going to go this way, but also that way. So if you put 0.5 moles in solution, not all of it gets dissolved. So it's a weak acid. That makes it a weak electrolyte. Then we look at this HCl. This is a strong acid. It should break apart into H plus and Cl minus ions. You should know strong acids and weak acids, or at least if it's not a strong acid and it is an acid, it's going to be a weak acid. Last but not least, we got this. This does not break down, it is not soluble. It's on the solubility rules. This guy, however, will break down into Mg2 plus and SO4 2 minus. It is soluble. Okay, so your question is, which would light the light bulb the brightest? Well, again, we're looking for an increased number of ions would tell us it's a better electrolyte. Over here we have 3 because we have 2 sodiums and 1 sulfate. Over here we have less than 2 because we know it's not going to break completely apart. Here we have 2, the H plus and the Cl minus. Here we have 0, and here we have 2. So the answer, therefore, is A. Next we look at this question. A gas in a balloon occupies 5 liters, 50K, blah, 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 blah. The first thing I should think of 2 things. Thing number 1, PV equals nRT. Anytime you see gas. So you should be like, is there a gas involved? Yes, then PV equals nRT. The next thing you should see is it changing? Because if it goes from one volume to another volume, if anything in that particular question changes, then you're going to be using P1V1 over N1T1 equals P2V2 over N2T2. In this case, we have pressure, volume, and temperatures. It doesn't say anything about moles, which means moles must be the same on each side. If they're the same on each side, they would cancel out mathematically anyways, so we don't worry about them. All right, now we can look at the problem itself. It says our initial pressure was 1 atm. Our initial volume was 5 liters, and our initial temperature was 50K. It's saying you double it. You're going to double the pressure to 2 atm. Originally it was 1, now we're going to do 2. It asks us to double the volume as well. So it's originally 5, now we're going to make it 10 liters. And then we're essentially solving for this temperature. So if we go and plug and chug, we're going to have our P1, which is 1 ATM, times our V1, which is 5 liters, over our T1, which is 50K. And we'll set that equal to 2 ATM times 10 liters over some kind of unknown, or T2. If you go about and do some math and solve for it, you will find out that T2 equals 200K. Another way to think about it is this. P1 V1 over T1 equals P2 V2 over T2. Well, if we have our P1, let's do it this way, or our P2, excuse me, is equal to 2 times P1, and our V2 is equal to 2 times V1, and we're going to solve for a new T2, so let's go ahead and ignore this and just set these two equations equal to each other. So we doubled the pressure, we doubled the volume. This and this tell you that there's an increase of 4 P1 V1 over T2. In order to maintain this ratio where these equal each other, this one must increase by 4. Mathematically, it has to increase by 4, and that's how we could also go about solving it. Number 5. So y'all, I messed up on this. I'm really sorry. I rounded wrong. I rounded in the middle of the problem. You're never supposed to do that. So I'm going to walk you through it relatively quickly and show you where I rounded. At the very, very end is where I rounded accidentally. So first we turn grams into moles. So we're going to divide this by 32.00 grams per mole. And for O2, you'll get an answer of 0.020312 mole. You do the same thing for N2, where we're going to divide this by 0.02 grams per mole. So we divide this one by 32, this one by 28.02, and in which case you'll get an answer of N2 to be 0.018558 mole. So what this is saying is, you got a balloon, and about 0.02031 moles is O2, and 0.018558 mole is N2. And I said, okay, what percent is N2? Because we know that the total pressure is 2.4 ATM. All we have to do is find the percent of one of these, and we can figure out the contributing pressure. So for example, if they were 50-50, then each one would contribute to our 1.2, or exactly half of this. Instead, let's go ahead and focus on the percent of this one. So to do that, we first, we want to take what we're interested in, 0.018558 mole of N2, divide it by the total moles. So essentially we're going to add this plus this, and if you add those two up, you get an answer of 0.03887 mole. And that's our total. And all we're going to do, this would give you about 47.74%, if I remember correctly, somewhere around there. And you multiply it times 2.4. Again, this tells you it's like 0.47. I don't have the exact number written, but 4774, I think. Don't hold me to it. So in other words, 47.7% is N2. Multiply it by 2.4, and you get an answer of 1.145. Here's where I rounded. I just said that that was 1.15. That's not. You look at the two numbers because we only have two sig figs, and our answer is 1.1 ATM. Moving on. Number 6, we kind of went over it in class. Essentially, an increase in temperature means it's an increase and average kinetic energy. If I would have been very smart about this, although this is actually technically correct, the question, I should have written average kinetic energy, just because you want to make sure that you're paying attention to the average kinetic energy, not the total kinetic energy. So the average kinetic energy of all the molecules. Okay, this dude, Hess's law. It's a bit of a beast, so I think I'll probably post a separate video to go over Hess's law problems in general, if you're having any trouble with them. In the meantime, what I'm going to do is just kind of walk through this very, very quickly. The main thing you have to pay attention to is the fact that these are solid. This solid and aqueous, and same thing, gaseous and aqueous HCl. So you're trying to manipulate and find some kind of way to add these equations up and get 2 aluminum plus 3 Cl2 gas, yielding 2 AlCl3 solid. And you're trying to cancel things out. Now remember, you add up everything on the reactant side and everything on the product side in order to do that. And you can flip, flop, etc. in order to get that. What you'll find you'll have to do right away is flip these two. So we're going to have AlCl3 aqueous going to AlCl3 solid, and then this sign will change to positive, 323. Another thing you'll see is you'll need to do it, multiply it by 2, because here we have a solid, here we have a solid, but it's only 1, and here we need 2. So we're going to multiply each of these by 2. Same with over here, times 2. All right, some other things that you'll see. Over here we have, let's see, 2 aluminum, that's looking pretty good. 3 Cl2, so we're going to need the Cl2 right here to be 3. So we'll multiply each of these by 3. This becomes 6, that works out really well. And times 3 over here. Then the HCl and HCl, well here we have 6 HCl aqueous, here we only have 1. So we're going to have to multiply these by 6 in order to get these HCl to cancel, times 6 over here. Now at that point in time, you're looking pretty good. So if you take this number, negative 1049, this number, which is negative 448.8, and all of these are in kilojoules. This one is negative 5535, and this one is positive 646, and you sum them all together, you will get an answer of negative 6387 kilojoules. Number 8, woo, we're getting through it. Number 8, this concept seems to have been lost on a few of you, so hopefully this helps get us through it. It says you heat an unknown solid to 90 degrees. So you've got this solid that has a mass of 43.70 grams, and you heat it up. It's hot. It's at 90 degrees Celsius. Then you go ahead and take that solid and you put it in some water. So let's go ahead and pretend. So we've got the solid, and you put it in water. Over here, the mass of the water tells you it's 50.00 grams. Expect this to be given to you in volume and use the density of water to determine the mass of water. That's a high probability something like that will show up. We've got our C. We know that that is 4.184 joules per gram K. And we know the change in temperature in this case because it was hot and the water went from being 50 degrees to 55.10 degrees. So it was 50 originally, went to 55.10. So our change in temperature is 55.10 minus 50.00, which gives us 5.10. Again, when you're looking at temperature, it doesn't matter if you're talking about Celsius or Kelvin, the difference, as long as it's a delta, can be in K or C. Okay, now over here, we know the mass was 43.70. We'll see what the C is, and delta T, we're gonna try to go ahead and figure out right now. We know that the final temperature for both of them was 55.10. So when this one let heat out, this one gained heat. So essentially we went from being 90 degrees, so delta is always a final minus initial. Our initial was 90. Our final in this case was 55.10, and our delta T overall was negative 34.90. Okay, so we've got MC delta T for this and MC delta T for this. Why? Okay, Q equals MC delta T, where Q is heat. So there's a few ways we can look at this. We can say, okay, look, we can figure out how much heat the water gained, or we can figure out how much heat this thing released, but we'd need the C in order to do this. So the part that a lot of people seem to be missing, or that we might seem to, that maybe I did a poor job instilling in you, is the fact that heat lost by the solid is equal to heat gained by the water. Whatever the solid lost, the water gained it. Another way to talk about this, you have to look at the signs of these things. In other words, if heat is lost, that's got to be negative. It lost heat. So the negative Q of the solid must equal the positive Q of the water. So now we can just go ahead and set this up. Our negative Q of the water, or the solid, excuse me, is MC delta T. In other words, 43.70 grams times C, which we don't know, times delta T, which is negative 34.90 joules per gram K. But check it out, this was negative solid, so we have to put a negative sign here. The negative of this is equal to the positive of the water. Well, we actually know all the variables for the water. We could have solved that in and of itself all alone. So we know the mass of the water is 50.00 grams. The C of the water you need to memorize, 4.184 joules per gram K. Memorize. And the delta T is 5.10 K. Now you can have everything that you need to go through and solve for this C. You should never end up with a negative C. And your C is going to be 0.6996, but this beautiful one had only 3 sig figs, and therefore your final answer should have 3 sig figs. You highlight these 3, ask if this is 5 or greater. It is. Just because it looks scary doesn't mean you should get rid of it. If you have $699.60, you would round it up to $700. In other words, 7.00 E negative 1 was your answer for this question. Last but not least, and thankfully pretty straightforward on this one. Remember, we just treat this delta H as part of the reaction, kind of like a stoichiometry problem. We see 4.6 grams of CO2, which we know we need to turn that into moles. 4.6 grams divided by 44.01 grams per mole will give us an answer of 0.1045 mole of CO2. That was right here, we're starting with 0.1045 mole. It's asking us about heat, so we gotta go over to this heat using stoichiometry. We start with 0.1045 mole of CO2. And if there were a coefficient here, we'd put it, but there's not. So there's for every 1 mole of CO2, again, if this had been 2 or 3 or 4 or 8, we would have put that there. For every 1 mole of CO2, we release 393.5 kilojoules. And this is how we do this whole problem. This will give us an answer of 41 kilojoules, and some of you are like, but the negative sign, you could have left this negative, but we have to pay attention to the fact that it said how much heat will be released or absorbed. So it's going to definitely end up being negative, which means because we could have left the negative sign there, it was released. So this is another way you might see it written in a problem. 41 kilojoules was released. If you put negative, it'd be kind of weird. Negative 41 was released, it's like 41 was absorbed. Anyways, hope this helped, and if it didn't, well, then that was a big waste of my time. 24 minutes and 36 seconds. Bye, y'all.